All right, for the last section, chapter 4, 7.4, we're going to talk about hyperbolas. And this definition is very similar to the ellipse with one slight difference. It's not a constant sum, it's a constant difference. So now we're going to take focus to some point on the hyperbola, to the other focus, D1, D2. If I subtract them, now this difference is going to be a constant. All right, so again, looking at our axes, notice things have changed a little bit. We have a transverse axis that connects the two vertices, so this is like the major axis for the hyperbola. And your conjugate axis, that's the minor axis from the ellipse for the hyperbola. Your distance A is still from the vertex to the center. Your distance C is still center to focus, but now notice, wait a minute, A will no longer be the longest side. C is now the biggest distance. And B is the same distance, center to that covertice. And while we're here talking about those covertices, you're going to notice our hyperbola does not touch the covertices, but we will need to use that point when building our hyperbola. So to find D1 minus D2, we're going to do the same thing and move the point P down to the vertex. So focus to vertex, that's F to center, that will be C, and center to vertex, that will be A. So that's the length of D1. D2 is going to be C minus A, just like we had in the ellipse. Wait, check that, that was A minus C. This is now C minus A. But if we take D1, C plus A minus, in parentheses C minus A, that minus sign will transfer, we'll distribute that into the parentheses. It's getting late here. So that's minus C plus A. So again, your constant sum, your constant difference are both 2A. Remember that. You're going to need it later on. All right. The other thing I want to point out here is now with that covertices, what we use those for is we have what we call an asymptote box or asymptote rectangle. So if you think about when we had the ellipse, we would graph the ellipse inside this rectangular shape. But now with the hyperbola, it's like you cut it at these covertices and you flip it out and force the curve to go to these asymptote lines. So you kind of get these parabolic looking shapes, but they're hyperbolic. And these asymptote lines, they're going to be B over A or A over B, again, depending on where the vertices and the covertices go. But so far in this case, from this point to this point, it's downhill, and we're going net down B to the right A. And over here, it's a slope of B over A, up B, right A. So that gives me the equation B over A times X. This, come back here, Y equals negative B over AX. Now, don't worry. Is it A over B or B over A? You'll never have to worry about that. If you graph this like we did the ellipse, well, we won't have that problem. So again, we're going to have vertical hyperbolas, horizontal hyperbolas. Vertical hyperbolas open up and down, horizontals open left and right. We're still going to do the same thing in terms of plotting A's, the B's, and the C's. It's just how we make the curves now. But again, now look at the equation. There's a change. The ellipse had a plus sign here. And they always had the x squared first, not anymore. The y can be first, so if my fraction with the y in it is positive, it opens up and down. And if my x squared is part of the positive fraction, it opens left and right. So now the a squared and b squared, they don't change. Now it's the x squared and y squareds that switch places. And the other thing you should notice is look at my Pythagorean theorem. It now has a plus sign. So here's a little note that you should make. Whether it's the ellipse or the hyperbola, the Pythagorean theorem always has the opposite sign than the equation of the ellipse or the hyperbola. The ellipse had a plus sign, Pythagorean theorem was with a minus sign. Hyperbolas have a minus sign in the equation, Pythagorean theorem is now a plus sign. Be careful when your center is somewhere other than the origin. Notice the tops change, and therefore you really got to say to yourself, find the x, change the sign, there's your h. Find the y, change the sign, there's your k. A lot of people will say, oh, here's my vertex or my center at k, comma, h. No, gotta be careful. Don't get these two mixed around. So again, say to yourself, find the x, change the sign. Find the y, change the sign when you want to write the center. And then the next thing you're going to notice is that my equation of my asymptote lines are different. Now we're using point slope form instead of y equals mx, if in case plus b, but the b is a 0. Oh, but that's going to be super nice because you'll just steal the y minus k binomial and the x minus h from the equation and just put the slope being multiplied to the x minus h binomial. All right, so let's go graph some of these. All right, in this case here, x squared is the positive fraction. This is opening left and right. No minus h, no minus k. Your center's at the origin, 0, 0. Underneath the positive fraction is the a. So a squared is technically 9. We're counting left and right 3. Those are my vertices. But I still need to look at my covertices, b squared being 16. I need to count up and down 4. Now, what do I do with my vertices? I literally, hopefully you can see this. Can you see the flashing purple rectangle? Those vertices and covertices are the midpoints of the sides of that rectangle. Once you draw in your rectangle, now you draw in the diagonals of that rectangle, and those are your asymptote lines. And remember how we use the arrows over here? Left and right 3, up and down 4. Well, your up and down arrow, that's your rise. Your left and right arrow, that's your run. So from the center, I'm going up 4 and to the right 3. Now, while I'm here talking about these asymptote lines, when you graph this by hand, when we get to the test, go to each corner and apply the slope. Up 4, right 3, up 4, left 3, down 4, left 3, down 4, right 3. And don't go any further than one application of the slope from each corner. The reason for that is your hyperbola will be so close to that asymptote line by the time you get to the edge here, you don't need any more asymptote line. So from the vertex, we're going to go out flat, turn to that asymptote line, and you will be there really close by the time you get to that end point of that one application of the slope. Then do the same thing down, same thing over on the left, up and down. And there's my hyperbola. To find my foci, again, we solve the Pythagorean theorem for C. Now we just take both denominators, add them together, and it really doesn't matter which order you write them in because we're adding. 9 plus 16 is 25. Square root of 25 is going to be 5, so we're counting left and right 5 to get to our foci. Remember, always approach the capital V's with your capital F. Finding your coordinates, same as before. Start with your center. Add and subtract 3 to the x-coordinate. Add and subtract 4 to the y-coordinate for the co-vertices. Add and subtract that 5 to the x-coordinate of the center to get your foci. And the other thing we're going to have to find now are the equations of your asymptote lines. So here we're going through the origin. Your y-intercept is 0, which you really don't need to put in plus 0. But you keep putting those arrows in. That's your rise. That's your run. Plus or minus 4/3 times x. All right, next example. Now, in this one, it's y squared over 4. Now the y squared fraction is going to be positive. So this hyperbola is going to open left and right. No minusing h or k to my x and y, so we're still at the origin for the center. Find your a's and b's, and again, a squared is 4, and we're underneath the y, so we count up and down 2. Plot that, label it with your capital V's. 25 is part of the minus fraction, so that's your b squared for the 25. Square root of 25 is 5. And we're underneath the x squared, so you count left and right 5. And again, you build that rectangular box. Draw in the diagonals. Again, rise plus or minus 2 over 5. So from each corner, up 2 to the right 5, up 2 to the left 5, down 2, left 5, down 2, right 5. There are my asymptote lines. Our vertices are up and down, so this is going to be really wide. So start here, literally barely touch the rectangular box, and turn right up that asymptote line, going in both left and right directions on top and bottom. Finding that foci, Pythagorean theorem, add the 25 and the 4 together to get 29. Square root of 29 is approximately 5.4. So we're going to count up and down about 5.5. 1, 2, 3, 4, 5.5. Foci are really far away from the vertices, which makes sense because the wider the hyperbola, the further the foci are from the center. Or center, I mean vertex. The closer the foci to the vertex, the skinnier the hyperbola will be. Finding my coordinates, again, everything starts at the center for my vertices. Start at 0, 0, add and subtract the 2 to the y-coordinate because we counted up and down. Counted left and right 5, add and subtract that to the 0 of the x-coordinate. Foci, plus or minus square root of 29 to the y-coordinate of 0. Asymptote equations, y equals positive or negative 2 over 5 times x. All right, I'm going to stop it here because I know the video is getting long.